Good afternoon, everybody. Appreciate the opportunity to share some of NASA's work in supersonics with you. So the title of my presentation is Breaking the Sound Barrier. As most of you are aware, Chuck Yeager broke the fictitious sound barrier in 1947, becoming the first flying the Bell X-1, flying supersonic in level flight. But that's not what we consider the real sound barrier. The real sound barrier is the noise from supersonic aircraft, sonic boom, that has essentially prevented supersonic overland flight and the establishing of markets for quiet supersonic commercial aircraft. So I'm going to talk about NASA's efforts to achieve supersonic overflight and prove its acceptability to the public. All right, so a little bit of history, some basic information about sonic boom. Talk about the progress over many years on finding a way to solve the sonic boom problem. How NASA researchers response to sonic boom sounds. Then we'll get into talking about our X-59 and the mission to demonstrate acceptable sound from supersonic flight. Conclude with some summary comments. All right, as I mentioned, first level supersonic flight, 1947. Sonic boom was quite a novelty at that point in time. There were air shows where sonic booms were demonstrated. Because we had very rapid development of supersonic military aircraft in the decade that followed. And as more and more operations began to take place, noise and damage concerns began to quickly arise. In the late 50s and early 60s, we had a number of supersonic commercial aircraft were proposed, given that there was already existing noise concerns. There were community studies that did indeed determine that sonic booms from the proposed commercial aircraft would be unacceptable to people on the ground, which led to the U.S. FAA's ban on supersonic flight over the United States, and an international limit, which essentially says you can't produce any sound from supersonic flight that may create an unacceptable situation for the public. So effectively a ban. Nonetheless, we did have commercial supersonic service from the Concorde from 1976 to 2003, but the aircraft only operated at supersonic speeds over the ocean. In 2003, when the Concorde was retired, that was effectively the end of what was the first generation of commercial supersonic flight. But continued interest in there's always continued interest in faster air travel. So NASA's research and really the vision of a community of researchers and companies across the world are that there will be a potential for an expanding market of civil supersonic flight, broadly accessible to the public, and continuing to contributing to a transformation of the speed of air travel. But unlike the Concorde, this vision for supersonic flight is broadly available to the public, but is also efficient, affordable, and environmentally responsible in terms of supersonic overflight, high altitude emissions, and landing and takeoff noise. Of those three, it's NASA's belief that the overland flight restrictions are really the unique challenge for supersonic aircraft. And because of the way airline operations work, they're the main barrier to achieving our vision for supersonic flight. The national research agencies such as NASA and the FAA, as a policy agency, have vital roles in enabling this vision from the perspective of not only developing technology, but also collecting and disseminating good scientific data that essentially supports the development of valid standards and regulations that protect the public but also enable innovation by industry. All right, sonic boom 101. Essentially, any airplane flying through the air is pushing the air out of its way. That creates a pressure signal around the airplane. It's a pressure disturbance. Of course, all pressure disturbances, all sounds are really just pressure disturbances. So that sound or that pressure disturbance from the airplane precedes the aircraft and essentially tells the air that it needs to start getting out of the way because something is coming. As you go faster and faster, the sound that propagates forward, the pressure that propagates forward, is compressed somewhat, and that's the kind of the Doppler effect that you hear once, like from a train whistle. But eventually, if your aircraft is traveling at the speed of sound, those pressure disturbances are no longer getting out in front of the airplane. So essentially, there is an instantaneous change of pressure in the forward in the direction of flight. And as you go faster than sound, of course, now you're outracing your pressure disturbance, and the pressure change reaches an observer instantaneously. And we call those instantaneous pressure changes shock waves. So, and the shock waves are responsible for creating the sonic boom. But sonic boom is not the sound of the aircraft breaking the sound barrier. In fact, it does not start until the aircraft is exceeding Mach 1, but it is created continuously as long as the aircraft is flying faster than Mach 1. So if you wish, it's a three-dimensional phenomenon. It's a sound, so it does travel out in all three directions, in all three dimensions. Some of it goes up. We're most interested in what occurs when that sound intercepts the ground. And as I mentioned, since it's created continuously, a large carpet of ground is essentially swept over as the aircraft flies. Noise is normally most intense directly below the aircraft and reduces as you go out to the sides. So very important to consider that sonic boom is a three-dimensional phenomenon. I'll try and keep that in mind because most of what I'll talk about now is more easily explained if we look at the phenomena in two dimensions. So you've got an airplane. It's flying at supersonic speeds. It's producing shock waves from the nose, from the wing leading edge, from the canopy, or from the cockpit, from the engine inlets, from all its components, essentially. So there's a shock wave system that you can measure if you look up close to the airplane with multiple shock waves. As that sound propagates from the airplane to the ground, because those shock waves are of different strengths and in different positions, they tend to start to coalesce. The noise does attenuate, it gets quieter, but the coalescence essentially rebuilds the sound. Eventually you wind up with a very stable signal consisting of just two shock waves with a large expansion in between them, and that's what reaches the ground. And because of the instantaneous nature of those two pressure pulses, that's what causes the boom boom of a sonic boom. If you plot that, if we draw that as engineers, we draw it, it looks like an N, so naturally it gets called the N wave, the N wave sonic boom signature. So again, looking at the airplane as it flies, again, the airplane accelerates to Mach 1. There's what's called a focus boom signature as the airplane transitions to supersonic speeds. And as it continues to climb and reaches its cruise condition, the boom kind of reaches a steady state value. Again, there's a primary exposure region directly under the flight path, or directly into the sides of the flight path that attenuates as you go further away from the flight path. But eventually the atmosphere causes the signal to essentially curve upward. So there's a sudden, or rather abrupt cutoff in the sound. It doesn't taper to zero. But also the atmosphere causes some of the sound that originally went upward to eventually curve and come back down. And that can be heard if atmospheric conditions are right, and that's called the secondary sonic boom carpet, and it can be quite some distance from the flight path of the airplane. And it was indeed a problem for Concorde even when it was decelerating and coming in from over the ocean. The booms could be heard quite farther inland given certain conditions. So let's think about how we would go about minimizing sonic boom. And lots of things have been tried over many, many years. Energy addition, heating, small explosions, flying at different speeds, accelerating, diving, etc. But in terms of a practical approach, if you look at how I just described an N wave is created, what you really need to do is up near the airplane is if you can design the airplane shape so that the position and the strength of those individual shock waves near the airplane are uniform and consistent. What happens is they do not merge, and you get maximum attenuation of each individual shock. So by the time the signal does reach the ground, the shock waves have been greatly reduced in strength, and you get something other than an N shape on the ground. And what was originally proposed is there were two shapes that were thought to have the best potential to reduce the disturbance. In one, you're trying to produce the minimum initial overpressure and then keep the pressure constant after that. And then another where you have a minimum initial shock and then you allow the pressure to rise more gradually to the maximum overpressure peak. And that second signal in particular was shown through NASA studies early in the 1990s to be very effective at reducing the annoyance to sonic boom. And we did that by essentially recreating those sounds in a booth, which, believe it or not, because of the way it was designed and didn't allow reflections and echoes, simulated the sound of a sonic boom outdoors. And we have test subjects sat in that little brick chamber, and we closed the door and we exposed them to different sonic boom signals. And if you look at the plot on the right, what you see is essentially how people rated the sound as a function of the difference between that initial shock and the total overpressure, and also a concept called the effect of rise time. Now, I mentioned that those shocks are instantaneous pressure changes, but after a long propagation distance, they interact with the atmosphere, so they become a little bit smeared, so they're not quite instantaneous and they have a slight rise time to them. Turns out the smaller the shock is, the more rise time it develops, which is a very good feature if you're trying to reduce the sound. So if you look at the figure that says, one millisecond of rise time compared to 3, again, you can see that the combined effect of shock strength and rise time has a marked difference, marked impact on how people rate the sound in terms of loudness. So we thought we were on the right track towards creating a signal that would be less disturbing. Now, how do you convert that into an actual aircraft design? So it was Al George and Richard Seabass in 1969, believe it or not, that proposed the initial mathematics that related the area distribution of the airplane to the shape of the ground signal. So if you could create that area distribution with the design of your airplane, you could create a shaped waveform at the ground. And that was the basic mathematics that was improved by NASA researchers Christine Dodden and Bob Mack in work during the 1970s and 80s, where they developed an iterative process essentially to shape an airplane to produce a shaped waveform. Those concepts and those designs were tested in wind tunnels, where we were able to flow supersonic air over a model of a quiet supersonic configuration and measure what the pressure would be near the airplane. As you can see from the figure, accounting for wind tunnel effects, that lo and behold, we were able to shape at least the forward portion of the signature to create something like a flat top, or a gentle rise configuration, gentle rise signature. By the early 1990s, we understood what kind of signals might create an acceptable noise level, and we understood the basics of how to design an airplane to create those noise levels. But the theory had never been proven in actual flight tests. So in early 2000s, a DARPA-sponsored program it did exactly that. Essentially set out to prove the theory of shape boom propagation in a real atmosphere, and we did that by modifying an F-5 aircraft to have a shape signature on the forward portion of the ground signal, and we compared it back to back with flight with an unmodified F-5, and lo and behold, the theory did work pretty much exactly as predicted. The lower left shows the predicted flat top signature in blue for the shape boom demonstrator, compared to an N-wave for conventional aircraft. And the larger figure in right shows what we measured. So this really was a significant step towards achieving quiet supersonic flight. But we really weren't out of the woods yet, because if you look at this signal, now this was a demonstrator, and we didn't particularly try to reduce the back end signal, but we were still the design theories up to that point were saying that there was little you could do at the back end of the signature to reduce the noise. So that needed to be addressed. And lo and behold, during the early 2000s, there was some interesting work done where essentially we took essentially somebody said one day, well, why are we trying to achieve a particular shape on the ground? What we really just want is a quiet signal on the ground. So let's try to let the ground signal and the design shape evolve simultaneously. And you can notice, looking at the upper right, we drifted towards designs that had a lot of small shocks in the signal in the near field, but again they're relatively small and they're relatively evenly spaced, so they would attenuate and not merge. And so lo and behold, that method began to point us in the direction of really making a significant impact on the loudness of the sonic boom signal and being able to produce more practical designs. So I won't go into detail here, but improved computational fluid dynamics, the way of essentially analyzing the flow field around the airplane to understand the shockwave position and what was causing the shockwaves, improved computing and improved techniques for exploring the design space, which enabled us to more rapidly assess multiple configurations and find good ones, all combined into development of a new quiet supersonic design process. And again, we first went to the wind tunnel and validated that the near field signals would produce the flow field and the shock pressure field that we wanted, that would give us the desired signal once it propagated to the ground. And our test measurements in this case very closely matched what our theory said we were doing, and we were now shaping the forward end and the back end of the signal. So that really led to what was considered a breakthrough knowledge advancement for quiet or quiet supersonic or low boom design, where we could go from, as it shows on the left, the classic Concorde N-wave, to a signal that's much attenuated, has much more rise time, as I mentioned before, and is potentially 30 or more dB quieter than the Concorde or any existing supersonic aircraft. Completely different signal. And we proved that the designs that we tested in the wind tunnel were not only just models, but they were conceptual designs that looked at integrated solutions, essentially, that could produce not only a low boom shape, which had to be the driving design parameter, but also were practical designs that could incorporate all of the other required features of an aircraft, including being quiet around the airport and being efficient at supersonic cruise. And you'll note, I've noted some of the features of quiet supersonic design here. And again, it really starts out from you really need to consider that you want to make a quiet low boom design right from the beginning. So that drives the total 3D shape of the fuselage, wing, fuselage and wing. The propulsion system installation has to be unique to mitigate the shocks associated with the engine inlet. And then the empennage design must control the impact of the lift of the configuration on the signature value. So that's unique and slightly different from what you might see on another supersonic. Other than that, the designs are not too radically different from what you might expect to see in a supersonic commercial airliner. This design was expected that it could address some of the barriers, or all of the barriers, to overland flight. And it's important to consider that by this point in time, even in the early 2000s, although no one had been able to show that a quiet signature was possible, that even for N waves, there was a lot of research that showed that creating a signal that was quiet in terms of its dB level and its effect on the human ear was really the only significant problem. If you looked at any of the effects that were originally potentially be attributed to supersonic aircraft, experience even with N waves showed that seismic triggering, avalanche triggering, building damage, effects from aircraft to aircraft were all negligible. And if you could solve the human response disturbance, then the door was open to practical supersonic overland flight. And here's just some of the other items going into acceptance by communities. And the upper left plot essentially shows the results of some of the earlier sonic boom overflight tests that were conducted from the 1960s up to the 1990s, and where the little smiley face is the level that we expect to get to with the new low boom designs. And essentially, I said there's no relevant data, because this data, you plot it on the curves of existing response, you're down. You're showing that there would be no response to these quiet sounds, which may be true, but needs to be validated with real data. So where do we get that real data? I already mentioned the early laboratory studies using the small sonic boom simulator at NASA Langley. The sophistication of those simulators has improved greatly over the years. Work with some of our industrial partners added a lot more realism and better reproduction of the noise. And of course, in the laboratory, what we can do is create repeatable and consistent test conditions to really study the elements of the sound that create annoyance. So we're understanding how things like the overall spectrum, the overall level, rattle, and vibration impact people's response. The conditions are not particularly realistic, even in our most sophisticated simulator, which is shown on the right, our interior effects room, which is set up like a normal living room. And we invite our test subjects to experience the sounds in there. It's not their living room, so it's good reproduction. It's very good scientific data, but it's not very realistic of someone's actual experience of the sound. So we really would like to. We're looking to do something outdoors, but of course we didn't have an airplane that really could produce a shaped, quiet signal in level flight conditions. And one of our researchers made some measurements, believe it or not, of the Spaceship One as it was diving back from its record-setting flight, and noticed that the signal that he measured was rounded and attenuated, kind of like our desired low boom signals. And he came up with the idea of, well, if we take a conventional aircraft, in this case one of NASA's F-18 research airplanes, dive it down steeply and just go supersonic briefly, essentially we create a pulse of sound that travels out nearly parallel to the ground. And because it travels such a long distance, it attenuates and rounds and gives us a fairly good simulation of a quiet signal. And it's a very repeatable attempt, and you can change the level by changing the dive position relative to your observers. The challenge with this maneuver is directly below the airplane. It creates a very intense sonic boom sound. So it must be done in an area such as the high desert around NASA's Armstrong Flight Research Center and Edwards Air Force Base out in California, where you can have a test community, but you can also arrange the maneuver such that the louder sounds don't impact any communities. So that's what we're able to do. We've done a number of research studies in restricted communities using that dive maneuver, looking at realistic structures and environments, people in living and working conditions, and different sizes of structure. And we're able to gather a lot of data, and not only that, but also look at the approaches to conducting larger community tests. And we took that step a few years ago to conduct our first large community test for response to quiet supersonic sounds in Galveston, Texas. We used the same F-18 dive maneuver, but in this case, by selecting a coastal community, we were able to expose the community to quiet sounds, but dump the louder sounds into the nearby ocean. And we weren't expecting to get particularly clear data about the dose response in this case, but we really were looking at addressing the risks that might, to conducting larger, even larger community tests. So things like how do you engage with the community, the necessary approvals, how do you recruit people to participate, how do you record the sounds in the community, and how do you deploy and maintain an aircraft in the field. And so we had a very successful risk reduction effort. And so we really were ready to take the next step to create fully realistic community overflights, exposing very large areas and very varied populations. And this is really the key data that we need to show that quiet supersonic flight can be quiet enough to be acceptable and allow the international regulatory community to establish limits for supersonic overflight sound, just as they establish limits for takeoff and landing noise of all aircraft. So that is our mission. That is our new low boom flight demonstration mission. And despite the rather awkward name. It's not about boom, it's about a quiet supersonic sound. But we're looking to create that key data that supports the development of a new standard that will open the market for supersonic flight. And this is a big challenge. It requires our new design approaches to be proven effective in flight. There is no data that exists yet to define those limits. So it's up to us to create that data, and the data must come from a large and diverse population. And perhaps most importantly, if the aircraft is truly going to be acceptable for global aviation, that standard has to be accepted internationally. So that is the genesis of our mission. There's 3 phases. Right now, we're in the process of building an experimental aircraft that incorporates the shaping features, and I'll talk a little bit about that on the next slide in more detail. But phase 1 is the design, the fabrication, the checkout flights, and what we call the envelope expansion, showing that the airplane is safe to fly. After that, phase 2 is the acoustic validation phase, where we prove that the quiet signal of the airplane is behaving as we expected it to in the design. So we'll measure the signal near the airplane to understand if we got the shockwave pattern right. We'll measure the signal on the ground to check the loudness level. We'll validate the tools that we use to predict the signal, so that we can plan. So that can be added to the planning for phase 3, which is once we know that the signal in the airplane, the airplane is safe to fly and safe to operate in the national airspace system, and we know that the signal is acceptable for community testing, we'll move into our community response testing phase. And as you can see, although phase 1 is ongoing now, preparations for phase 2 and phase 3 are already in progress, and we expect to start our first community test in fiscal year 2024. And that's a lot of planning that needs to go on, essentially scaling up that Galveston test about 100-fold in terms of measurement capabilities and noise exposure design and recruiting and conducting community response testing. So all this planning and activity we view as a systematic approach leading to our desire to conduct community overflight tests. So a little bit about the airplane itself. As you can see, this is a single-seat X-plane, supersonic research aircraft designed for a few key specific purposes. And that's how you go about doing an X-plane, is you try and only do the absolute minimum that's required to meet your 1 or 2 goals of your effort. So in this case, this airplane, we want to replicate the signal and the noise levels which are expected from future larger commercial supersonic aircraft. And we want to do that in a way so that we can fly it not in a dive maneuver, but in operations that are more like aircraft and cruise and represent the flight operations of supersonic aircraft. So if you look at the airplane, it's 100 feet long. It weighs about 25,000 pounds. It goes Mach 1.4, and really those are all just features that are essentially required to meet that first requirement. You can see the features that I pointed out earlier: the 3D shaping of the vehicle, the long slender nose, the propulsion system installation, the unique empennage arrangement, in this case incorporating a conventional tail, but also a small T-tail, and the canards located forward by the cockpit. Although the airframe shape is completely new and unique, it makes use of a lot of existing internal components to minimize the overall cost of the mission. So an existing engine and many, many parts from donor aircraft. NASA has partnered with Lockheed Martin to build the X-59 QueSST aircraft, and that effort is ongoing now. It's a picture of the manufacturing floor a few months ago. There's been a lot of progress since then. We're getting close to the final mate of all the components of the airplane. We've essentially procured an existing military aircraft engine to power the airplane. There's a lot of suppliers that are involved in creating this airplane. And as I mentioned previously, there's a lot of components from donor aircraft that are known quantities, but they still must be fitted and integrated and properly have their systems properly incorporated into the design. So the work is going well, despite the challenges of designing a complex airplane like this, and of course, the COVID-19 pandemic. We're slightly delayed from our original first flight date, but we expect to fly the airplane sometime early next summer in 2022, or the middle of next summer, sorry, 2022. So in conclusion, there's continued interest in commercial supersonic flight, and it's really an unfulfilled promise to the traveling public for improved mobility, improved global mobility. There's an incredibly long history and rich history that has led us to the point we've made a breakthrough on the achievement of quiet supersonic flight that's applicable to large integrated supersonic aircraft configuration design. But before those limits can be lifted, large-scale community testing is required to fully characterize the response to these sounds. And it's NASA's commitment, and NASA and the Low Boom Flight Demonstration Mission's commitment to the international community to apply this data that's required to create new supersonic en route noise standards and open the market for future commercial supersonic flight.
So we've seen data on how sonic booms affect humans. Has there been any studies on how sonic booms will affect animal life?
Yes. The previous larger program, which was called the High Speed Research Program, in the late 1980s and 1990s, that was a big concern, and there were numerous studies done for different types of wildlife, marine mammals, birds, etc. And to date, no effects of sonic boom sounds on wildlife have really been identified.
Okay, so to kind of follow up on that, with all the resources you're devoting to making a quieter supersonic aircraft, is that just because it's a nuisance to people, or are there other more severe consequences we're trying to mitigate?
No, again, as I said earlier, in the lead up to the Concorde and the USS, there were the severe consequences, and believe me, everything was thought to be a possibility. As I mentioned, even earthquakes triggered by sonic boom, and there were studies done, on the seismic effects of sonic boom. And there were studies done on whether sonic booms could create lasting structural damage to houses, whether they could interrupt surgeries or things like that. And there were literally hundreds of studies done, and all of those other effects were proven to be negligible compared to, and really the only thing that was left was the fact that it was still an annoyingly loud sound.
Okay, and we did have one or two folks note that the X-59 does not appear to have a front windshield. So, how does the pilot see what's going on in front of the aircraft?
So very interesting. Yes, the shape of to achieve the shape required for a quiet signal, you need to have a very slender nose, which essentially makes a front windshield useless because of the glare associated with the sun angle hitting the windshield. So we've created a external vision system, as it's called, and essentially, as I'm sure you're aware, aircraft cockpits have over the years incorporated more and more electronic technology, and they now have both heads up and heads down displays, which essentially provide the pilot all the information he needs to conduct operations without the window. The only thing that hasn't done yet is to take the window away yet. So the X-59 has essentially a large high definition computer display in front of the pilot that provides him with his external view. And that system has been again tested in the laboratory and tested in flight and shown to be effective not only for operations in the modern airspace system, where most flights are conducted on instruments anyway, the equivalent of flying in bad weather, but also in conditions where the pilot needs to spot other aircraft visually. And the interesting thing about using a computer display is you can mix sensors. You can put radar data and infrared data, which really can enhance the view of the outside world and actually improve the safety of flight.
How does the X-59 design, how is that going to scale up for future commercial level aircraft?
It's interesting. So if you recall from the presentation, we didn't start from a demonstrator design. We started from a real, a full-sized aircraft design, and our wind tunnel tests showed that the results of those design efforts, which were indeed for full-scale aircraft, small supersonic airliners up to about the size of the Concorde, the design technology did work. So effectively, some of the challenges were really scaling it down so you could have a piloted aircraft that utilized a lot of off-the-shelf components and could actually achieve that design shape. So there were compromises made during the design of the X-59, which may not necessarily have to be made for larger airplanes. Essentially, have more real estate, larger shape to work with in choosing your design parameters for your low boom design. There has been a lot of knowledge gained about the design process for supersonic aircraft during the X-59 development. Really, and again, I mentioned that the sonic boom is a three-dimensional problem. So if you're going to achieve a low boom design, not only does it have to give you the shape signal right directly below the airplane on the center line, but also to the full extent of the carpet. So improving our optimization methods so that we can produce a fully 3D design that is quiet is something that really has been perfected during the process of the X-59 development, and that indeed will be applicable to future generations of airplanes.
All right, so it looks like we don't have any additional questions in the chat, so we're going to go ahead and wrap it up. Thank you all for joining us today. Thank you to Mr. Peter Coen for joining us and telling us all about the X-59 program. Very exciting development. I'll be interested to see how this all plays out. So please join us next week on Thursday, March 11th at noon. We're going to have Dr. Evan Reiter, MD, who is the medical director of the VCU Smell and Taste Disorder Center. And he is going to be talking about COVID-19 and smell loss. when we can no longer wake up and smell the coffee. So you can register for next week's talk at smv.org. Each talk is free to attend and is open to the first 300 registrants. And again, please take note, next week will be Thursday and not Wednesday. So again, you can register at smv.org. It's free to attend to the first 300 registrants. Thank you again for joining us today. Until next week, stay safe and stay curious. Thank you all for joining us.